So we're continuing to study and review for the final exam. And so let's look at the following question. It says, find the equation of the line tangent to the curve y equals the square root of 9 minus 4x when x is -4. So there's two things that we need when we're trying to find the equation of a line. We need the slope and we need a point. So we have the x value of our point, and we can find the y value of our point by going in and plugging in -4 wherever we see an x in that function. And so if I looked at y of -4, this is equal to the square root of 9 minus 4 times -4. So this is equal to the square root of 9 plus 16, which is the square root of 25, which is 5. So we know we have a point on the tangent line, which is going to be -4, 5. Now we need to find the slope of the tangent line. So we want the slope of the curve at x equals -4. So we know we can find the slope of a curve by taking the derivative of our function. So let's just rewrite y a little bit to help us take the derivative. And so let's rewrite it as 9 minus 4x, and this is all raised to the 1/2 power. And so now when we take the derivative, we can use the chain rule. So taking the derivative of our outer function, we have 1/2 of the inner function, 9 minus 4x. Subtract 1 from our exponent, so 1/2 minus 1, that gives us -1/2, times the derivative of the inside. So the derivative of 9 minus 4x is just -4. So let's clean this up a little bit. We have the derivative here is equal to 2 goes into -4, -2 times. So I have -2 in my numerator, all over, and let's bring down that negative exponent to make it positive. So we have the square root of 9 minus 4x in the denominator. We need to find the slope at -4. So we're going to go in and we're going to plug in -4 wherever we see an x in this function. And so we get back -2 all over the square root. We saw before plugging in -4, that gives us the square root of 25. And so this gives us back -2/5. So we now have a point and we have the slope -2/5. So you can use your point slope formula. I tend to like to use y equals mx plus b. Let's plug in what we know from our point, what our slope is, and then we can solve for b. And so our y value of our point is 5. So we have 5 is equal to our slope -2/5 times x, which is -4, plus b. So we have 5 is equal to 8/5 plus b. So subtracting 8/5 on both sides, I see that I'm going to need a common denominator. So we can get a common denominator of 5. So 5 with a common denominator of 5 would be 25 over 5 minus 8/5 is equal to b. So we get b is equal to 17 over 5. So the equation of our tangent line going through the point, or the value x equals -4 on the curve, is going to be y equals our slope -2/5 x plus 17/5. So the next example, we have y equals the natural log of 5x plus 2, and that 5x plus 2 is raised to the 4th power, all over the square root of x squared plus 5. We want to find the derivative of this. So looking at this, this looks like it would be a mess if we just went in and did the quotient rule. Within the quotient rule, we're going to have to use the chain rule multiple different times. And so this is where, and I wrote this out a little wrong, which is good because it would make it better if it wasn't like this. This is where if we use properties of logs, so this is the natural log of this whole thing. This is where using properties of logs makes this a lot easier. So if we have a log and we have a log of some division, we can break it down as the difference of those logs. So this is the natural log of 5x squared plus 2 raised to the 4th power minus the natural log, and I'm going to rewrite that square root as a 1/2 power. So natural log of x squared plus 5 all raised to the 1/2 power. We also have a property of logs that we can bring our exponent down front. And so this gives us y is equal to 4 natural log of 5x plus 2 minus the natural log of 1/2 natural log of x squared plus 5. So taking the derivative now, we get the derivative of y dy dx is equal to, so we're going to use the chain rule here. So we have 4 times, well, when we take the derivative of a natural log, that is 1 over what you're taking the natural log of, which is 5x plus 2 in this case, times the derivative of the inside, the chain rule, which in this case would be 5. Minus 1/2. And now when we take the derivative of the natural log of x squared plus 5, we're going to look at times 1 over what we're taking the natural log of x squared plus 5 times the derivative of the inside. And the derivative of x squared plus 5 is 2x. So we can clean it up a little bit. We have in our first fraction 4 times 1 times 5, so that's 20 all over 5x plus 2. And notice that this 2 here from the 1/2 cancels from that 2x. So we have minus x all over x squared plus 5. So using properties of logs a lot of times can be really beneficial to rewrite it and then take the derivative. And there were times where we had an ugly function that we were taking the derivative of, where we might take the natural log of both sides so that we could rewrite it and make it simpler. Okay, so we have another function we want to take the derivative of, and our function is 4x squared times y plus x squared minus 6y to the 4th equals 5. So this is an implicit form of an equation, and it's impossible to solve for y, get it by itself. And so we were going to use implicit differentiation. So remember with implicit differentiation, when we take the derivative with respect to y, that's a function of x. And so we have to think of it as a chain rule and multiply it by dy dx after we take the derivative. So looking at this first piece, 4x squared times y, I'm going to have to use the product rule for that. And so let's take the derivative of the first 4x squared. So the derivative of the first 4x squared is 8x times the second function, which is y, plus the first function, which is 4x squared, times the derivative of a y. Well, the derivative of y is 1, but we took it with respect to y, so this is times dy dx. Okay, so we just took the derivative of that first term, plus now taking the derivative of x squared, that is 2x, minus, and so taking the derivative of 6y to the 4th. So bringing our exponent down front, we have 6 times 4, so 24. Subtract 1 from our exponent, so y cubed. Again, we took the derivative of y, and y is a function in terms of x, so we have to multiply by the derivative of the inside, dy dx, is equal to derivative of 5 is 0. So once you go through and use implicit differentiation, we now want to get dy dx by itself. So there's two groupings that have dy dx in them. So let's leave that on this one side, and let's get everything else on the other side. And with the piece that we're leaving those dy dx on the one side, we can actually factor that out, and that's what we're going to want to do. So let's factor out dy dx from that 4x squared dy dx, which leaves you with just 4x squared, minus, and let's factor out the dy dx from the 24y cubed dy dx. So that would just leave us with 24y cubed. Equals, so we're gonna move over this 8xy to the other side. So this is minus 8xy. And we're gonna get the term 2x to the other side. So that's minus 2x. We're almost there. And so let's divide both sides by 4x squared minus 24y cubed. And we would get dy dx is equal to, maybe at the same time we can do a little factoring, because I see things are going to cancel. So that numerator, if I pull out a negative 2x, that would be left with 4y plus 1. All over. And so let's look at factoring when we divide by this. And we can pull out a 4 from both of those terms. So if I pull out a 4 from both of those terms that I'm dividing by, I get x squared minus 6y cubed. So it only simplifies a little bit. That 2 and then 4, 2 goes into both. And so now we found the derivative dy dx is equal to x times the quantity 4y plus 1 all over x squared. Oops, have a 2 up front, 2 parentheses x squared minus 6y cubed. So let's not forget to bring down this negative right here. And so that should have been a negative in front of that x. So our next example in front of us, y is equal to tangent cubed of 5x, and we want to find dy dx. So it might be helpful if you rewrite this tangent cubed of 5x. This is the same thing as saying we're looking at the tangent of 5x quantity cubed. And so when we take the derivative, we're going to use the chain rule, and we're going to have to use that chain rule twice. And so if we look at the chain rule, we get the derivative of y dy dx is equal to, bringing our power down front, 3 of the inside tangent of 5x. Subtract 1 from our power times, and I'm going to do it in a minute, but not take it yet, the derivative of the inside tangent of 5x. So this gives us 3 tangent, I guess I can write it as tangent squared now. So 3 tangent squared of 5x. So when we take the derivative of tangent of 5x, the derivative of tangent, recall, is secant squared. So this is going to be times secant squared of the inside 5x times, we have to take the derivative of the inside of our function 5x. And then the derivative of 5x is just 5. So we found the derivative dy dx is equal to, let's just multiply this 5 times the 3 out front. So we have a 15 tangent squared of 5x times secant squared of 5x. Okay, so the next example says use the first and second derivatives to determine all extrema and inflection points for the curve y equals x to the fifth minus 30x cubed plus 6. So if we want to find our extrema, we need to figure out the derivative and find when the derivative is equal to 0. And there's a couple ways that we can test that. We can see where it's increasing and decreasing to see if we have a local max or a local min, or we can plug that into the second derivative test. And that sometimes works, sometimes it doesn't. Okay, so we're going to need to find the derivative of this function y. And so dy dx, our derivative, this is equal to 5x to the fourth minus 60x squared. And the derivative of 6 is 0. So this is defined everywhere, so we're okay there, but we want to find where this is equal to 0. So notice that we can factor out a 5x squared from both of those terms. So let's pull out a 5x squared.
Wouldn't it be minus 90x squared?
Yes. 3 times 30 is 90, not whatever I put it. So if we pull out a 5x squared, we are left with an x squared minus 5 goes into 90. Let's see, 1 time, 18 times. And we're setting this equal to 0 to get our critical values. So when is 5x squared equal to 0? Well, that's when x is 0. And then x squared minus 18 is equal to 0. Well, x squared equals 18. We could take the square root of both sides. We get x equals plus or minus the square root of 18. Or square root of 9, because that's a factor of 18 is 3. So plus or minus 3 root 2. Okay. So let's plug it in. Well, yeah. Well, it's saying to use the first and second derivative final. So I'm not sure if they want us to use the second derivative test. Let's just use the second derivative test. Let's find the second derivative. And so let's leave our derivative in non-factored form, 5x to the fourth minus 90x squared. So if we take the second derivative, that gives us 20x cubed minus 180x. So the second derivative test says that we can go in here and we can plug in our values. And I think it might be easier. Let's see. I'm just thinking it maybe it would be easier if we kept it as square root of 18. Let's leave it as negative root 18. So if we plug it in here, we got 20 all times negative square root of 18 quantity cubed minus 180 all times negative square root of 18. We're just worried, or we're just curious, is this greater than 0 or less than 0? If we got back that this was equal to 0, the test is inconclusive. So we have the square root of 18. I need to figure out what that is. And then I'm going to cube that result. Times 20. So the first piece, if I plug that in correctly, this is negative 1,000, approximately negative 1,527.4 plus, now if we look at, oops. So notice here, I don't know. Yeah, I'm okay. Plus, so 180 times the square root of 18. And so that gives us 736.7 about. So 763, I don't know. 0.7. So I can see that this is less than 0. Since that's less than 0, that tells us it's concave down there. And so if it's concave down, that tells us that negative root 18 is a local max occurs. That doesn't tell me what the local max is, it just tells me that it occurs there. And then we do the same thing and we plug in positive square root of 18. That's going to give us positive approximately 1,527.4 minus, that's going to give us 763.7. I can see that that is definitely greater than 0. And so we know that square root of 18, it's concave up, so a local min occurs. And we also need to test 0. That one's a lot easier, right? Actually testing 0 though, if we plugged in 0 into the second derivative, notice that we get back 0, which tells me my test is inconclusive for 0. And so we're going to need to test values on each side to see, is it increasing or decreasing there? So let's look at something between negative root 18 and 0. So maybe let's look at x equals -1. So if we went in there and we plugged that into our first derivative, just to see if it's increasing or decreasing. Well, I get 5 times -1 raised to the 4th power. So that's going to just be 5 minus 90 times -1 squared. So 5 minus 90, that is going to be less than 0. So we know it's decreasing here. And so let's look at looking at the other side, about x equals +1. Again, if we plug in 1, this is an even function. If I plug in 1, I'm going to get the same thing as if I plugged in -1. And so the derivative evaluated at 1 is also less than 0. And so it's decreasing. So x equals 0 is not, a local extrema does not occur at x equals 0. They wanted us to find, determine all the extrema and the inflection points for the curve. And so we can find where our inflection points are by looking at where is our second derivative, which we have right here. Where is our second derivative equal to 0 or undefined? Well, our second derivative is always defined. And so let's factor out a 20x from both of those terms. So if we pull out a 20x, we're left with x squared minus 9. So 20x, we're looking at when is that equal to 0. So x minus 3, x plus 3 equals 0. So possible inflection points are x equals -3 0, and positive 3. And so we just need to see, is it changing concavity on each side of those numbers? And so we're going to need to look at our number line again. But this time we're plugging these into our second derivative to see if we're positive or negative on each side. So if we look at x equals -4, and if we looked at it as the derivative, second derivative, just so we can think about positive and negatives, as that factored form, 20x all times x squared minus 9 might help us a little bit. So at -4, we have 20 times -4. That's a negative number, right? All times -4 squared, which is 16. 16 minus 9, that's a positive number. So this is less than 0. So we know that it's concave down on the left of x equals -3. So let's choose a number between -3 and 0. So how about -1? If we plug that into the second derivative, well, -1 times 20, that's a negative number. All times -1 squared is 1, and 1 minus 9 is also negative. So this is less than 0. I'm sorry, that's not less than 0, it's greater than 0. And this is concave up. And so because it's changing concavity at x equals -3, -3 is an inflection, where an inflection point would occur. Same idea, let's look at x equals 1. We plug it into the second derivative. We got 20 times 1 is 20, so that's a positive number. 1 minus 9, that's a negative number. This is less than 0, so we have it is concave down. So we're changing concavity from concave up to concave down at x equals 0, so 0, an inflection point occurs. So one more, let's look at x equals 4. So the double derivative evaluated at 4, well, 4 times 20 is positive. And then we have 4 squared, which is 16. 16 minus 9 is also positive. So a positive times a positive is greater than 0. And so this is concave up. So those are all -3, 3, and 0. These inflection points occur at. Let me just pause for a second. Okay, so they didn't find the y values of those points and left it like this, except that they pulled out what they could from underneath the radical like we had done before. So we know that -2, not -2, -3 root 2. Local max and +3 root 2 was where our local min occurred. Okay, so our next problem says analytically determine the absolute min and absolute max of f of x equals x cubed minus 2x squared on -1, 1. And that's a closed interval. If our function is continuous on a closed interval, and I know f of x equals x cubed minus 2x squared is continuous everywhere, it's a polynomial, then by the extreme value theorem, this has to have an absolute max or an absolute min, and that may occur at one of our endpoints. So first thing that you want to do is you want to find the derivative, and we want to find our critical points. And we're only looking at critical points that fall between -1 and 1. So let's take the derivative of that, f of x. So derivative of x cubed is 3x squared. Minus the derivative of 2x squared is 4x. So we're looking at when is 3x squared minus 4x equal to 0? We can factor out an x, which gives us 3x minus 4 equals 0. So setting each piece equal to 0, we have x equals 0. And 3x minus 4 is 0. If we added 4 divided by 3, we get x equals 4/3. 4/3 is the same thing as 1 1/3. So notice that this is not inside, is not contained in there. And so we're not going to even look at that 4/3. And so this is where we want to plug this back into our original. We want to use our endpoints, so -1 or any critical numbers that fall in between -1 and 1. So 0 and 1. And we're plugging that back into our original function. So if we plug in -1, wherever we see an x in our original function, we get -1 cubed, which is -1, minus 2 times -1 squared, which is 1. So that's -2. This is going to give us back -3. So at x equals -1, we have a point of -3. Plugging in 0, we get back 0. Plugging in 1, we get 1 cubed, which is 1, minus 2 times 1 squared, which is 2. This gives us back -1. So the largest y value is where our absolute max is going to occur, and our smallest y value is where the absolute min occurs. So we can see that we have an absolute max of 0 at 0, and we have an absolute min of -3 at x equals -1.